my name is Diasha. Welcome to the third lesson in this series, Chemical Reactions 1. So far, we have used the metallic bonding model to explain why metals have special physical properties. In this lesson, we are going to focus on the chemical properties of some metals. Now, some of the reactions we will look at today are quite spectacular, so be ready to make careful observations. Of course, we will need to write balanced chemical equations too. But before we begin with our investigations, let's first find out where we find metals on the periodic table. If you look carefully at the periodic table, you will see a zigzag line running from the top left corner to the bottom right corner of the table. This line separates the metals from the non-metals on the periodic table. These elements close to the dividing line are called semi-metals. They're special because they have some metallic properties and some non-metallic properties. Now, the metals are further divided into groups on the periodic table. Group 1 metals are called alkali metals. Group 2 metals are called alkaline earth metals, and the elements in the large block in the middle of the periodic table are called transition metals. For the experiments we will be looking at in this series, we will choose examples of metals from each of these groups for our investigations. In this lesson, we will be focusing on the reactions of the group 1 or alkali metals. From the group 1 metals, we will use lithium, sodium, and potassium in our experiments. Okay, let's get going. This is what we would like to achieve today. By the end of this lesson, you should be able to describe the observations, name the products, and write down a balanced chemical equation for each of the reactions that you see. Before we begin the experiments, let's have a look at a model of a single atom of sodium. This atom has a large atomic radius and the outermost electron is far away from the nucleus. You should also notice that when a sodium atom loses one electron, the ion that forms will have a stable electron structure. You may remember that sodium atoms have a low first ionization energy. This means that a small amount of energy is required to make sodium lose one electron. When we put all of these facts together, I think we can predict that all of the group 1 metals will be very reactive. Let's start experimenting to see if our predictions are true. As you look at the experiments, remember that these metals are not found as pure elements in nature. The pure metals we will be using have been extracted from ores dug out of the ground. A variety of chemical techniques are used to extract the reactive elements from stable compounds. These types of reactions are all called decomposition reactions. But in the reactions we will look at, the metal combines with other elements to form compounds. These types of reactions are called synthesis reactions. Have a closer look at the elements we will be using today. The alkali metals react spontaneously with water and with air. They must be stored in a waterless, airless container. They are stored in paraffin. When using the metals for experiments, they must be handled with care. Always use tongs or tweezers to hold them. Under no circumstances must the metals be handled with bare hands. They can be cut using a scalpel or a sharp knife on a hard surface. In the first part of our experiment, we would like to find out what alkali metals look like. As you observe, look out for any color changes and try and estimate the softness of the metal. First, the lithium is removed from its container. Do you notice that lithium is a dark gray, shiny metal? It is also fairly hard, but can be cut with a scalpel. Next up is the sodium. Can you see that sodium is a light gray, shiny metal? It is fairly soft and can be cut easily with a scalpel. Did you also see that it goes duller very quickly after being cut? Lastly, we will look at the potassium. It is a similar light grey shiny color as sodium, but it goes dull almost immediately when you cut it, making it difficult to see the natural color. It is very soft and is cut with ease. Now, whenever you do experiments, it is always a good idea to draw up a table to record your observations. In the next part of our experiment, we will have a look at how alkali metals react with oxygen. This is the experimental procedure that needs to be followed. A gas jar is filled with pure oxygen and sealed temporarily. The cut piece of metal is placed in a combustion spoon. The metal and oxygen are the reactants in this experiment. It is gently heated in the flame of a Bunsen burner for a few moments until the metal is burning, and then the metal is plunged into the gas jar full of oxygen. The new substance formed in this reaction is called the product. Let's begin our experiments, starting with lithium. Lithium burns with a pinkish red flame. In oxygen, it burns more vigorously and with greater brightness. Can you see that the product formed is a white powder? Do you know the name of the product that forms during this reaction? Well, when lithium and oxygen react, the product will be a combination of these two elements. The metal name is written first and the non-metal name second. Lithium and oxygen are the only two elements in this compound, so the name of the second element is changed slightly from oxygen to oxide. So, the product formed during this reaction is lithium oxide. We will retain the lithium oxide for further tests in later lessons. Now let's take a look as the same experiment is done with sodium and potassium. As the sodium starts to burn, you should be able to observe that it burns with a yellow-orange flame. As expected, it burns more vigorously and more brightly in oxygen. A white product called sodium oxide is formed. Now we try potassium. Potassium burns with a beautiful lilac or purple flame. The lilac flame is much brighter when potassium burns in pure oxygen, and the reaction is more vigorous. Again, the product is a white powder that will be kept aside for further tests. The name of the product is potassium oxide. In each of these experiments, we have observed a chemical change, and now we need to accurately represent this change by writing a balanced chemical equation. To start with, let's check if we can write down the correct formula for the reactants and the products formed. We'll start with the reaction of lithium and oxygen to form lithium oxide. Lithium loses one electron to become stable, but oxygen needs to gain 2 electrons. This means that 2 lithium atoms react with 1 oxygen atom. So, there has to be 2 lithium atoms and 1 oxygen atom in the formula. We indicate this by writing a 2 as a subscript next to the chemical symbol for lithium. So, the chemical formula for lithium oxide is Li2O. Remember, we can never change this formula. We know that sodium and potassium are in the same group as lithium, and they react with oxygen in the same way. In other words, 2 sodium atoms will react with 1 oxygen atom, and 2 potassium atoms will react with 1 oxygen atom. How would you write the chemical formulae for sodium oxide and potassium oxide? Here they are. Sodium oxide is written as Na2O. Potassium oxide is written as K2O. Now let's write chemical equations to describe the chemical changes we have observed. Remember, the first step is to write a word equation for the reaction of lithium with oxygen. When we read this, we say, lithium and oxygen reacts to form lithium oxide. Lithium and oxygen are the reactants, and lithium oxide is the product. The next step is to translate the word equation into a chemical equation. We can replace the word lithium with the symbol Li. The symbol for oxygen is O. But remember, oxygen is a diatomic molecule, so we write O2, not O. We already know the formula for lithium oxide, so the chemical equation is Li plus O2 reacts to form Li2O. The last thing we need to do is to check that the chemical equation is balanced. This means that the number of atoms of each element at the start of the reaction must be the same as the number of atoms of each element found at the end. The law of conservation of mass must always be obeyed. Do you remember what the law states? Does our equation obey this law? Okay, let's do the counting. There are 2 oxygen atoms on the left-hand side of the equation, but only 1 in the formula of the product. This equation is unbalanced. To balance the oxygen atoms, we need another oxygen atom in the product. But the formula of lithium oxide, Li2O, cannot be changed. We can only change the number of particles of lithium oxide found in the product. Since each particle of lithium oxide has 1 oxygen atom, I need 2 particles of lithium oxide in the product. I can show this by writing a 2 in front of the formula. Now the number of oxygen atoms is the same on both sides of the equation. But can you see we have a problem with the lithium atoms? In total, there are 4 lithium atoms in the product and only 1 as the reactant. Can you see that we need to have 4 lithium atoms in the reactants? We can show this by writing a 4 in front of the Li. This chemical equation, 4Li plus O2, react to form 2Li2O, is now balanced. Have another look at this balanced equation. The numbers in front of each of the formulae tell us the ratio of how the substances react. This means that the ratio of lithium to oxygen to lithium oxide is 4 is to 1 is to 2. This ratio is in the simplest form. If I write the same equation as 8Li plus 2O2 react to form 4Li2O, it would be balanced but not correct. Scientists always write balanced chemical equations in the simplest ratio. Here is your task for today's lesson. Write balanced chemical equations for the following reactions. Sodium plus oxygen react to form sodium oxide. Potassium plus oxygen react to form potassium oxide. Make sure that you do this task and have it ready to check at the beginning of the next lesson. Until then, goodbye.
Yeah.